Thanks very much, James, and thanks everyone for coming. Also like to offer a special welcome to those from outside GA who've come along. Thank you. It's nice to have you here during Science Week, and I hope you enjoy the presentation. My name's Nick, and today I have the pleasure of talking to you about you, me, and geodesy. My mum sent me this photo recently, this picture on the left-hand side, and actually comes from an old newspaper clipping when I was finishing up in Year 12. The local paper was doing reports on students leaving Year 12 and asking them what they wanted to do into the future. And the article mentions something along the lines of wanting to use satellites to measure and understand the Earth. So I suppose I've been lucky that for a long time I've always kind of known what I wanted to do, but not particularly sure which aspect of it that I wanted to specialise in. So I originally thought about being an astronaut, but then when I used to go to like the Royal Melbourne Show, I always hated the things like the gravitron, so I didn't think I was really going to be cut out for the rigorous high G speed test that they have to put people through. So as a kid, instead I bought a telescope, and with money that I had from doing a paper round very early in the morning. And I still remember the first day I set it up. I was very excited, put on my beanie and duffel coat in the middle of winter in Melbourne, went out in the backyard, and I'd been looking up in this book on the moon that I had about the first crescent moon. It's apparently the best time to look at the moon because the sun's hitting it at just the right angle and the craters appear to be really big and well defined. So based on this picture that I saw in the book of the moon, I went outside and I'm expecting to see this beautiful first crescent moon with the crescent on the right hand side illuminated. So of course I got outside and I see this. See the moon illuminated on the left hand side. It's all back to front. So I stared at the moon for some time, stared back at the telescope, playing with the lenses, think I'd inverted something incorrectly, and then quickly came to realise that, you know, we come from the land down under. So it was that moment I tilted my head, of course. It felt like watching a Monty Python movie. You've got to tilt your head to understand it sometimes, but tilted my head and then, of course, the moon's illuminated on the right-hand side. It was one of those aha moments for me, I suppose. It's like I get it. You know, it's this concept that you start to understand and you realise your position in the world. But as many of you I'm sure would have realised, as soon as you have one of these aha moments, it's quickly followed by so many more questions because you recognise that the Earth and the things around us are much more complex than you'd ever thought about before. So this one question leads to so many other questions. And questions like, how can I use information about the illumination of the moon and knowing a time to help figure out where on Earth I am? And of course I'm not the first person to be thinking about this. For thousands of years people have been using celestial objects like the moon, the stars and the sun to help them understand time and to navigate. A great example is the Aboriginal people who used to use the stars like waypoints to help them travel thousands of kilometres for ceremonies and trade. And many of the routes that they identified are still used today through treacherous environments as well, travelling through deserts, and we use those for major highways or routes for telephone lines. So very important background to where geodesy is coming from. Also in terms of Western civilization, they developed technology like Harrison's clock to help them understand time better when they were travelling. That allowed them to determine their longitude, and along with other information they could position themselves. So throughout history, being able to measure time and our position have allowed us to navigate, explore and discover. And in more recent times this statement still holds true. The only thing that's really changed is the technologies we use and the applications that can come from it. So what I'd like to talk to you today is about the what, why, how and wow of geodesy. So I want to start with the what and the why because I fully recognise that there's probably a lot of people in this room, if you've heard of geodesy, even those who have heard of geodesy, not quite sure what it is or maybe why it's important. I then want to get into the how. How is it done without equations? And then look at the wow, look at some of the opportunities that geodesy is likely to provide us into the future. So let's start with the what. Well, geodesy is the science of measuring the shape, orientation and gravity field of the Earth and how that changes over time. So we make these measurements of the Earth to try and compute an accurate three-dimensional model of the Earth. And these models can then be used to do things like uniquely identify our location, identify things around us and how to get to them, changes in the land, the oceans, the ice and atmosphere over time. So one of the fundamental aims of geodesy is to provide the foundation or the framework to reference our coordinates. And for this reason, we refer to it as a coordinate reference frame. And by defining this coordinate reference frame, what we're attempting to do is compute the shape, the orientation, and the gravity field of the Earth and how they vary over time. So what I want to take you through today is how we try and compute some of these things. And we'll start with size in a minute, but before we get into that, what I want to do is try and help you understand the why. So building on this idea of foundations that I mentioned, think of geodesy like the foundations of a house or the frame of a house, necessary to keep it stable over time. So my dark blue circle there in the centre represents geodesy as that foundation. And science and applications can then be built on those foundations. One of the ones that you're probably most familiar with is positioning and navigation. So as I said before, these are things like where am I and how far away are things that I care about, and then how do I get there? Another application that you might be less familiar with is accurate timing and accurate time transfer. So global positioning system satellites, which you're probably familiar with, are actually very accurate clocks which are orbiting the Earth. And this means that they can be used as a time source or to transfer a sync time over very large distances. And many critical systems utilise this technology. In terms of banking, that's one excellent example. There's billions of dollars of financial transactions that are happening at lightning speed all the time. And stock prices adjust to the news, and therefore time is pivotal to know what's happening, who bought things, and at what time they bought them. There's actually companies who vie to have the shortest route using optic fibre cables between their systems and the stock exchange. So in this case, geodesy helps twice. It's providing the timing for which you can timestamp financial transactions, and it's also helping them define the geodesic, which is the shortest distance between 2 points. It's also important for things like mobile phone technology. The spectrum that mobile phones operate on is limited, so you need to be able to jam in pieces of information into this spectrum, and that's all tagged with time. So the more accurately you can timestamp something, the more efficiently we can use that spectrum. And then there's positioning, which you're probably most familiar with. It's actually the time difference between the signal being propagated from GPS satellites and reaching your receiver on the ground that allows you to compute your position. So an example of this is, imagine that you're sitting on top of this satellite. Based on the information from one satellite, it only allows you to position yourself somewhere along that circle. So you need more than information from one satellite. So if we add in another satellite, you can see that you get 2 intersection points, but it's still not enough to determine your position. Once we add in the third and the fourth, however, it allows you to compute your position, and that is your latitude and your longitude. Okay, so geodesy is not just timing, it's not just positioning, it's not just navigation, but it also has significant influences in areas like public safety and disaster management. And geodetic techniques play a significant role in these areas. For example, with respect to seismicity, information from geodesy can help us detect strain build-up over tectonically active regions over time and help measure the movements that these earthquakes may cause. This isn't just the sharp movements that you might expect with earthquakes, but we actually have what we call seismic zones throughout Australia, where we go and observe campaigns at these sites over time, and we can detect these slow slip strain accumulations that are happening throughout the Earth. It's also very useful for things like understanding tsunamis a little better and observing environmental hazards. And a good example of that is the Fukushima earthquake. There were some amazing articles that came out after the Fukushima earthquake and tsunami which showed that the GPS network in Japan could actually detect the pre-seismic before the earthquake occurred, the co-seismic as it was happening, and then the post-seismic changes that were happening to the Earth over time. It's also very useful for things like volcano monitoring. We have a very good team here within Geoscience Australia using space-borne radar techniques with GPS to help understand the build-up and release phase of volcanoes. You can actually see volcanoes effectively breathing over time as the magma comes in and out and it gets released. So that flows into the Earth and climate science side of things as well. The satellite observations we take are able to detect millimetre scale trends in the ocean and land height. And this has influence in areas of science like climate change, using radar to detect ice loss, ice mass loss in Antarctica, and into other areas like post-glacial rebound. So as that ice flows off a glacier, for example, you can actually detect the Earth rebounding using GPS, and you see this uplift signal in GPS observations. In terms of oceanography, helps with understanding changes in sea level from using satellite altimetry and tide gauges. It can also be helped to understand the atmosphere, using GPS to detect changes in the atmosphere for extreme weather events. And actually we have a team within Geoscience Australia who are using this information and feeding it to the Bureau of Meteorology, so it feeds into weather forecasting as well. It also helps us understand groundwater changes. You can actually detect groundwater changes within the Earth just using space gravity techniques. With respect to industry, precise positioning plays a key role, and geodesy plays a key role. In industries such as agriculture with self-driving vehicles, precision sowing, so effectively you have these tractors that can drive themselves and make the most efficient use of the land by ensuring that they're not going over the tyre treads from the previous year and making efficient use of the soil. And also monitoring of crops by drones. I've seen these drones that can fly out, they do remote sensing to detect whether or not a certain crop needs pesticides sprayed on it or not. And it picks and chooses where it does the spraying. In terms of engineering and mining, bridges and tunnels, you wouldn't have bridges and tunnels without geodesy. They start on two sides and you've got to meet in the middle, hopefully at about the millimetre level. And it'd be a much longer process if you started from one side and you weren't quite sure where you're going to end up on the other side. Also plays a key role in precision guidance of autonomous mining equipment, and I'll touch on that a little bit more later on. And for identifying resources, it's a key component of what we do here at Geoscience Australia, help identify where resources are. In terms of shipping, it also helps to provide safer and more profitable shipping. The last one I want to touch on is height. Height's another key component, and it's actually from satellite gravity missions that we can measure changes in the Earth's gravity field over time. So why is that important? The reason is because gravity data is pivotal to underpinning our reference system for height, because fluid flows in accordance with gravity. So we need to understand that very well. And differences in the Earth's gravity field are important to understand for the design of water and sewage systems, for example. It also plays a key role in helping us with tsunami warning inundation and flood events, or the flow of groundwater. So I hope from that quick overview you can see that geodesy is actually providing the foundation for many fields of science and many applications. So if you ever get asked, geodesy, what have you done for me lately? Well, I hope you can now answer quite a bit. In recognition of this, in 2015, the United Nations General Assembly adopted a resolution entitled Global Geodetic Reference Frame for Sustainable Development. So Australia and the Pacific nations played a very important role in the establishment of this resolution with our very own Gary Johnson, who's here today as co-chair of the working group who helped establish this. Stuart Minchin from Geoscience Australia is also an Australian representative, and also the gentleman in the middle there, Fatasi, who's one of our colleagues from Tuvalu, who we cooperate with on the Pacific Geospatial and Surveying Council through an Australian aid project. So it was very good to see people from our region playing a key role in the development of this resolution. What this resolution aims to do is provide a mandate for countries, and it's really designed to help improve geodetic infrastructure, which is going to be necessary to support science and society into the future. It also aims to assist to meet some of the United Nations Sustainable Development Goals. Geodesy will support many of the nations by tackling some of these goals like climate action, clean water and sanitation, industry, innovation and infrastructure, and sustainable cities. So this is just further demonstration that the importance of geodesy to society is far more than what we might think of in terms of positioning and navigation, but it comes into these other areas. We've also got engagement with the World Health Organization on a working group related to this, so it's spreading far and wide. Okay, so we've covered a bit of the what and the why, so now I'd like to start touching on the how. How do we do this? How do we try and understand the Earth a little bit better and measure it? So we'll start with a bit of context. Here we've got Earth orbiting the Sun, third rock from the Sun, and the orbital period of about 365 days. Pretty simple, right? Let's see if we can get some modern technology to work here. Answer's no. I'll skip that. I'll show you at the end. But what I will show you is this picture, which is what I was attempting to show you the movie of, which did work before. Effectively what this is showing you is you've actually got the Sun, which is much more complex than a static body. It's actually hurtling through space at about 70,000 kilometres an hour. And it's the Sun's gravity field that's dragging the planets of the solar system along with it. So this Sun's firing out and you've got this vortex of planets which are orbiting the Sun as it's travelling. Furthermore, the Earth is actually being pulled by the Moon as well. So you've got this give and take happening. So it's actually quite complex. And from all of that, what we're trying to do is measure the Earth's size, orientation and gravity field. So we can't just use one technique to try and measure this. We actually need a whole number of techniques. So geodesists need a toolkit. Alright, so let's start by looking how we can measure things like the orientation rate, orientation and rotation rate of the Earth. Well, it's exceptionally hard to do while you're sitting on it. Think of yourself as sitting on the top of a football that's just being kicked through space. And you're trying to measure the way it's rotating and where it's moving through space over time. It's hard to do it using reference points that are actually on the football. What you need is reference points from some faraway place that are independent type reference sources. So to do that, we use reference sources called quasars. And these reference sources aren't on Earth. They're a long, long way away. And they're so far away that it's, for all intensive purposes, it's pretty safe to assume they're not moving. What these quasars are actually supermassive black holes which are surrounded by this orbiting disk of gas. And as the gas is being sucked into the black hole, it actually emits radiation. And this radiation can get detected by satellite dishes on Earth using a technique called very long baseline interferometry. So how it works is based on the time it takes for the radiation to be emitted by the quasar and to reach the two different points here that we have on the Earth's surface. You can actually use the difference in time it takes to reach the dishes to compute the distance between the dishes on the Earth's surface. And you can do this to detect millimetre trends in the continental plate movement of the Earth and helps us understand the size of the Earth. It's also very useful to help us understand the orientation of the planet. So the Earth spins on its own axis, the red line running through the middle, but it also has this other rotation that takes about 26,000 years to take place, and that's called precession. And that changes the tilt of the Earth's axis over time. Okay, so we've learned some information about the size and orientation of the Earth. How about the centre of it? How about the centre of your reference frame? This centre of your reference frame is actually the centre of the mass of the Earth. And SLR, satellite laser ranging, is actually a very useful technique to help us understand this. And it's another technique we need from our toolkit. How SLR works is it actually fires off very short pulses of light from stations that we have here on Earth to these, what I like to think of like space bling, these big giant golf balls that are hurtling through space, and you get a return of flight measurement. So you get a pulse that gets sent up and then the pulse that gets sent back can be received on Earth. And that helps us understand the distance between the satellite laser ranging stations, of which we have one here, which is Mount Stromlo. That's actually pulsing to the moon there, doing lunar laser ranging. And it can also be used to help us understand the gravity field of the Earth. So as the satellite moves from its current position to the next position, you can actually see that it's getting drawn in towards the Earth a little bit, and that means that it's moving over an area of the Earth where the Earth's mass is higher, so it's getting pulled in towards the centre of the Earth. And if you have a number of these measurements from around the Earth, you can actually use it to detect the centre of the mass of the Earth. Okay, so far we've used very long baseline interferometry to help us with the size and satellite laser ranging to help us understand the centre, but we've still only got a very sparse data set, and what we want to do is have a denser data set to improve our description of the global coordinate reference frame. So this is where global navigation satellite systems comes into it. And we have thousands of these pillar types that we've got down here in the bottom right that can detect global navigation satellite system signals from this whole range of constellations that are shown here in the top right. So the Global Positioning System from the US is probably the one that you're most familiar with, but they're not the only constellation of navigation satellites that we have. The Europeans also have Galileo, the Russians have the GLONASS system, and the Chinese have the Beidou system. And there's also 2 regional systems from India and Japan that improve the signal quality over their countries. So Australia's in quite a good geographic location to make best use of all these different constellations and improve our positioning capability within Australia. So this is an example of the GPS constellation. They're satellites that are orbiting at about 20,200 kilometres above the Earth's surface, and they're transmitting signals that allow you to compute your time and position. So there's about 31 satellites in orbit, and there's normally about 7 or 8 in view at any given time. So given that you need 4, you've always got a few redundant observations that help you with your positioning capability. Of course then, you've now got all the other constellations, which makes a very messy picture, which improves your capability again if you've got a receiver that can detect them all. So when studying cartography at university, my cartography lecturer used to harp on about Gestalt. And I don't know how many people have heard of Gestalt, but it essentially means the whole is more than the sum of its parts. And I think that really helps explain the power of what we're talking about here with geodesy. We're using complementary techniques, and we combine them all together to help us define this coordinate reference frame so that we can position ourselves and make use of these applications. So here's an example where you've got you can define your latitude and your longitude and your height above this coordinate reference frame, our reference ellipsoid here, to, for example, compute your position on the top of a mountain when you're doing a walk on a Saturday afternoon. The kind of data that feeds into this, the VLBI, which are the yellow stars that I made reference to, satellite laser ranging are the green diamonds, and the red dots are the GNSS. You can see that although we've got a large number of observations, particularly in Europe, in Australia we have less so. So if you're actually trying to compute your position with respect to a global reference frame, you could be a very long distance away from any of these reference points that goes into defining what that coordinate reference system actually is. So to get around this, what we do is actually establish a national datum, which is like a national coordinate reference frame. So to do this, we get a denser number of these global navigation satellite systems, cause stations we call them. They're continuously operating satellite constellation observatories throughout the Australian continent, and many of those are actually sites that are used in the global coordinate reference frame. So this provides the link between the national datum and the global coordinate reference frame. What we do is we then add about 2 million measurements, which has been happening over the last few years with work done here within Geoscience Australia and also our collaborators within the state and territory governments, to define a mathematical model. And what we do is we feed all this data in and do what they call a national adjustment to try and compute the coordinates at about 300,000 locations throughout the country. So this is a way of propagating that global reference frame down to a national datum that's actually useful for users and provides them with access to a highly precise and accurate datum. Okay, so we've now got our geometric surface, which is our national datum, and the beauty is that it's simple, it's precise, it's useful for GNSS because you can run around with a GNSS receiver, detect your position in a matter of minutes. But the problem with it is that water doesn't actually flow downhill on this surface. Water actually flows downhill according to gravity. And the Earth's gravity field isn't as simple as that geometric shape. I had a university lecturer that used to refer to the Earth's gravity field like an oddly shaped potato. And he's not far wrong because it's different, and it can be different by up to 100 metres in different areas. So for this reason, we actually need a separate surface that we use, a separate reference frame that we can use for heighting in the country. And this national reference system is based on gravity, and we call it the Australian height datum. And as I said, the difference between the geometric and the gravimetric can be up to 100 metres, and you can see in Australia has quite a complex signal of this low mass in the southwest to a high in the northeast. So we get a trend of between about minus 70 metres in the bottom left to about 90 metres in the top right. So in order to convert from your very simple GPS signal, you actually need a model to do a conversion to get you to something on which water will flow downhill. And this is why over the last number of years we've been working on the development of geoid models. The most recent one, Geoid 2020, is due to be released very soon, and it provides uncertainty along with the transfer in height between the 2 points. So the beauty of this is it actually enables a combination of the speed and efficiency that you'd get with GPS and GNSS to the practical requirements that users have for making sure that fluid flows downhill. So from everything we've talked about so far, I think you could appreciate that not all of this can be done by one country or one organisation. It's actually done by a whole range of services, one of which is the International GNSS Service. It's actually a voluntary federation of over 200 self-funded bodies, including GA, universities and research institutions. So the mobile phone applications and maps that you make use of are actually using a lot of the open access data that's provided by organisations like this. So whenever you've got a child sitting in the back seat and you are in a foreign part of town and you want to find the nearest McDonald's to give them a happy meal and give yourself some peace and quiet, and you're using satellite navigation to get there, you can be very thankful to these services and the information that they provide. Okay, so we've discussed the what, the why and the how. Now I want to do a brief presentation on the wow. What's geodesy likely to provide us into the future? What might be coming next? And I say might because that's the bit I'm most excited by. We don't actually know what a lot of the things are that people are going to use precise positioning for into the future. What we're aiming to provide is the infrastructure to allow people to come up with great business opportunities. So I suppose you could say, like Oprah Winfrey, what we're trying to do is provide precise positioning for everyone. You get precise positioning, you get precise positioning. We can't give out cars, but we hope we can give out this. And we want to make sure that we can get precise positioning everywhere for anyone at any time at the centimetre level. And what that will do is actually enable improved access to GNSS data and products for existing and new industries. And very briefly how this works is that the user segment in the middle there are actually still getting their satellite signals from the GNSS satellites, but that information is also being sent to the cause stations that we have down here on the bottom left-hand side. So that's reaching stations where we know the position of those stations very, very accurately. So what we can do is, based on the information coming from the satellites, we can determine what the correction is at that point. We know what the information, we know what the coordinate should be. Any difference that we're getting from the satellites is actually a correction. So all that information gets processed through a processing and correction service, and that can be delivered via the internet, or it can also be delivered by satellite. So we can send that data to an uplink station, up to a different satellite, then propagates that correction back down to the user. And this enables people who are outside maybe internet coverage to reach the capability of getting centimetre level positioning anywhere in Australia and the marine jurisdiction. So in terms of applications, some of the ones that you're probably all already aware of is mass market. So you, with your mobile phone, you can currently get, it's got a cheap antenna normally in this, allows you to position yourself to about the 5 to 10 metre level. The expectation is within the near future you'll be able to use precise positioning to get you down to the centimetre level using your mobile phone. And some of the testing that's already been done using some new infrastructure that we have and a satellite-based correction service, already getting down to that 0.5 metre level. So this is a real game changer because what it does is provide precise positioning in the hands of everyone, not just the spatial professionals who traditionally have had access to very expensive technology to get access to it, but it's now going to be in everyone's mobile device. So some of the benefits of this is augmented reality. So it's effectively holding up your phone and getting the camera showing you what's happening through your camera and what you can see, and then it's propagating pictures up over the top to give you new information. And the one that we're probably most familiar with is Pokemon Go, but I'm excited by the other information that's likely to come out as a result of augmented reality. To give you information like construction zones, taxis, flood history of an area, can give you information about tram times. There's already some applications out there like Yelp Monocle that lets you hold your camera phone up and you can look through your screen. It gives you markers of reviews for bars and restaurants that tell you what your friends and family like when they travel to that region. The other interesting thing, it allows access for things like underground services. Can you imagine, it's currently very hard to find underground services like electricity, telephone lines, sewage. If you could have someone come out with an iPad and was moving the iPad around just to try and figure out where they had to trench, it might avoid them digging up your whole backyard into the future. The applications aren't also limited to the land environment, but also the marine environment. There's parts of port operations that are already becoming automated, and I read some articles recently where the owners of these sites are saying, well, if you're not operating an automated port, you're going to go out of business. So this is becoming a very fast reality. It also provides safer navigation and improved tracking of your container movements. One of the amazing ones, I had a chat to the gentleman who runs the hydrographic service at Port Hedland's Ports, and he was talking about the under keel clearance system that they use. So that's the thing that allows them to determine how much draft have I got underneath the boat to allow me to actually get out the port. And by being able to measure it using precise positioning instead of the inaccurate positioning they had in the past, they're now able to get out about an extra 200 million tonnes of iron ore each year just from being able to enable that precise positioning capability within the port. The other one that you're probably familiar with and hearing a lot about in the media is autonomous vehicles. There's already 10 car companies that have these in production. There's also 7 states in the US that have enacted laws which enable autonomous vehicles. Perth has a driverless bus that I've seen pictures of that goes up and down the Perth foreshore in South Perth. And in 2016, the South Australian Parliament enacted a bill that allows on-road trials of autonomous vehicles. So they're really trying to lead the way. In a recent article I read, there's a major Chinese internet company that's announced that it's going to have artificial intelligence chips in autonomous vehicles by 2020, and Google is working on similar technology. GNSS is obviously only one of the requirements, along with like laser sensors and radar and cameras, but it's a very important role for positioning, speed, navigation, and also keeping the car in the centre of the lane. But autonomous vehicles aren't just limited to the roads, they're also used within the mining industry. Rio Tinto, for example, have an operations centre in Perth, and from that one central location, they're actually able to operate their mines, ports and rail systems all from a single location. And they operate 73 trucks, which are transporting iron ore 24 hours a day across 4 different sites. Aviation sector. They're another one who are, particularly at regional airports, that are likely to be able to capitalise on precise positioning in the country. It should improve their positioning down to about the 2 metre level in the horizontal and 4 metres in the vertical. And that will really help them with improved vertical guidance for landing, particularly in difficult conditions. The other important aspect is that there's research going on to look at higher integrity positioning. So how do we make sure that the signals that are getting reached at the aircraft are actually correct? So that takes some extra background processing and corrections to be done, and a lot of that work is being undertaken here within Australia and within Geoscience Australia. The one I'm probably, I wouldn't say most excited by, but I find quite interesting is the drone technology. At the moment, again, they're kind of seen as a bit of a toy, but I think they're going to become a much more useful tool in the years to come. And for things like agriculture and forestry, as I mentioned before, with the drones that can fly around and do remote sensing of the crops. But also for services like Amazon Prime Air, which have come out recently, and they're talking about being able to deliver packages within 30 minutes using small drones. And there's a trial of this already happening within Cambridge in the UK. The last one, agriculture. Precision agriculture were one of the first to pick up on precise positioning with their own capabilities within their farms, or sharing amongst farms in the area. Over 80% of grain farmers already use precision technology for things like auto steer. So this improves the land efficiency, water costs, and also helps reduce diesel costs by up to 50%, which is very significant. By 2020, it's expected that there'll be a $773 million improvement in productivity from precise positioning. So the applications that require precise positioning also require an accurate datum. And it's an important thing to remember that your data can only be as accurate as your datum. So there's obviously examples where some users are actually going to require a time-dependent reference frame rather than a static one that we currently have. A good example of this is the fact that the Australian plate is actually moving at 7 centimetres a year in the northeast direction. So in order to have, for example, autonomous vehicles that want to keep themselves in the centre of the lane, they're actually going to need a time-dependent reference frame which is continually updated to make sure that that can happen. And that's linked with the maps and the other data that they need to keep the cars on the road safely. So one of the things that we're starting to think about here at Geoscience Australia is how can we bring in all these different data types and define and establish a time-dependent reference frame in the country. So we can use the techniques that we've talked about before, the GPS and the SLR and the VLBI, but as you'd remember, they're a disparate data set and they're sparse. They're still sparse if you're looking to define time-dependent reference frame. What we actually need to do is bring in imagery, essentially. And this is an example of what you can do using spaceborne, what they call INSAR. It's a spaceborne radar technique that effectively allows you to create maps of surface deformation over time. And one of the things we're looking into is how can we bring in data such as this into the development of a time-dependent reference frame. Okay, so I hope you've enjoyed the why, what, how and wow of geodesy, and I hope you have a better understanding of the impact geodesy has on your life and mine. The world we live in is pretty complex and amazing, and it's the fact that we have foundation sciences that maybe don't get talked up as much as other glitzy sciences. These foundation sciences actually underpin and support other areas of science and society. And what we're endeavouring to do is to continue to improve the capability of what we can do within the geodesy section and throughout the world to measure the Earth and hopefully measure it more precisely to even enable more applications into the future. So as I mentioned before, this work isn't done by just one country or one organisation. But I should say GA, I think, does its fair share. You could say we punch above our weight when it comes to geodesy globally. And this is largely due to this wonderful bunch of people that I'm very proud to call colleagues. So I got some of their photos, but some of them a bit shy and I had to put their names up. I couldn't get access to their photos. So thank you to this group of people. and thank you for your time. Happy to take any questions.